Hello, my name is John Morgan. I am Director of the Simon Center for Geometry and Physics here at Stony Brook University. And we are at the Simon Center today. We have Rob Kirby, Nigel Hitchin, who will be interviewing Sir Michael Atiyah about his life in mathematics and more generally his life. Gentlemen.
Okay, well, Michael, we're here in the Simon Center for Geometry and Physics. Do you think it's a golden age for the two subjects, or was that long ago in Newton's time?
It's very difficult to recognize a golden age when you're inside it, actually. When you get a bit of perspective, it helps. But I think it's been going sufficiently active for some time that we are living through something of a golden age. How big an age it'll appear, a century later on remains to be seen. But right at the moment, it looks an active subject area, and that's why this centre has been built. And I think correctly, it's a focal point for a very exciting activity right at this moment. But posterity may have different views.
So mathematicians are used to viewing all sorts of objects as spaces, which means like importing the geometrical viewpoint to different areas of mathematics.
Yeah.
So you think the main import from physics is a language or a set of metaphors for us to look at our own subject, or is it more than that?
I think it's more than that. The notion of space is, in some sense, fundamentally where we live and move, and has been for thousands of years. It has gone through different eras with the Greeks and then modern ideas and physicists, and it evolves. It doesn't always mean the same thing. It increases dimension by giving one or two more here and there. It can change its shape by curving. So I think space but it's part of our visual imagination, and we use it to a great extent because our brains are very well attuned to seeing things and thinking in terms of 3 dimensions. So I think it permeates mathematics and physics, and it embodies the essential parts of a lot of physics. So I think it's more than just a notation or a symbolism. There's something rather deep about it.
But then do you think physicists have a different vision that we can benefit from as pure mathematicians?
Oh yes, no question. I mixed a lot with physicists over the last decades. Physicists have a lot of intuition coming from the results of their training, experimental data, what happens in the physical world. I've had physicists explain to me, how some complicated phenomenon happens. You put a magnet here and it floats around in space. And so, they have a lot of wealth of intuition based on concrete experience, based on real physical world, which they've honed and tuned and developed. A lot of it is mathematical, but a lot of it is intuitive. And that mathematicians don't generally have. So part of this interaction is to learn from the physicists. I don't mean learn in a formal way. You learn by osmosis, by talking to people and absorbing their instinct. And I think that's sort of been going on now for some decades, and a lot of mathematicians who have become a bit more educated, let's say, about the way physicists think and aren't quite as critical. Physicists tend to think in much more intuitive, non-rigorous terms, which doesn't mean it's not precise in any way. Mathematicians learn to accommodate that so they can communicate.
Do you think it's possible or is it desirable for us mathematicians to go through the whole process of learning quantum theory the way that a physicist would as a graduate student? Or is that counterproductive?
Well, for older mathematicians like me and even like you, it's a bit late.
Yeah, that's true.
If what you're trained in when you're young sticks with you for life and helps to make your background. Later on, you can learn a few bits here and there, you can widen your knowledge. You can't really re-educate yourself from the ground up. With the younger generation, it's a bit different. They have a choice at what stage they want to learn their physics, their mathematics, and you may get a new generation of hybrids who are really half mathematicians and half physicists in some deep sense. But in general, I think it's useful to have different points of view. The mathematician has a point of view based on his intuition, his experience, which uses the wide range of things in mathematics, some of which are outside physics. And so that's a compliment to what the physicists bring. I don't think it would be a good idea for all mathematicians to clone themselves on physicists, go into the lab, put on their lab coats, get their hands dirty with what. That's where you just turn out second-class physicists. I think it's important they keep their own perspective.
Would you say it's easier for physicists to morph into mathematicians, to move in that direction, than vice versa?
In some sense, yes. It depends, of course, which physicist you're talking about. If you're talking about the kind of physicist you meet in the mathematics corridor, yes, he's moved a long way already. if you look at physicists, you know, out in the world, practical physicists who deals with wires and what used to be called valves, no, because they've got a long way to go. But the younger generation of physicists who become very theoretical and much fundamental physics is now extremely mathematical, automatically they have to know mathematics to master their own trade. And so it's a small step for many of them to go over and learn a bit more about new mathematics. And they learn it much better if they know its relevance to their field. Learning it in abstract, saying I'm going to learn a book on abstract algebra without motivation is very difficult. Learning about new subject where somebody tells you is highly relevant to what you're doing is much simpler. You can relate, you connect up. So, but I think amongst the sort of people on the frontier, it's probably easier for the physicists to pick up mathematics, because mathematics and physics is a much more vague a notion. How do you pick up intuition without having gone through it all? How do you learn, you know, to get a feel for the things? That is more difficult, I think. So I think you're right. It's easier one way than the other.
Yeah.
What about geometry and physics in your own mathematical life? When did that begin?
Well, you know, when I was a student, because I was a student in Cambridge, and in those days, you learned half the course was about pure mathematics, half of it was applied mathematics, including some theoretical physics, Maxwell's equations. So I got a basic training, but I went to lectures by famous people like Drakh. But I was going to be a pure mathematician. Some of my friends drifted off, became theoretical physicists. I became a mathematician. We met again later, many years later on. And at that stage, I wasn't really very interested in physics. I dabbled with it a bit. And later on, I got interested in some aspects which I realized had to connect with physics. But I was not really much involved with physics until I turned 40. I don't know exactly, but I mean, it was then things started to happen which brought the physics much closer into the mathematics, and then I got more seriously involved. So that's probably been going for about 30 years. But in the first part of my life, I was definitely felt like a pure mathematician with a mild interest in physics. I would talk to physics a little bit, but not seriously.
Did this changeover occur about the same time that we discovered the physicists were actually dealing with vector bundles and connections, and in their own language with Christoffel symbols, and you say around 1972 or 3?
It was a very definite period, and I remember it was sometime in the early 70s, I think. And I remember going over to MIT to visit some of the physicists there, and when we discovered that what we mathematicians were doing was very similar, almost identical in technical terms to what the physicists were doing, for totally different motivation, with totally different description, and totally improved. So, and then we suddenly realized that we were talking about the same thing from different angles, and there were people around who said, well, yes, you should know this, because... And so a very, very short period of time, the dictionary started to evolve, people explained the terminology, and you know, but it met even at the earlier stage when we realized they were doing the same thing, but had no idea where it came from in physics and what the foundations were. We met at the top of the building instead of the bottom of the building. Later on, we had to go down and learn what was in the lower floors. But it was meeting right on the very frontier of the subject. And that's one of the interesting things that happened. In the past, mathematics and physics have interacted, but usually the mathematicians have interacted with physicists. Well, the mathematician comes along after the physicist has got all the interesting results and says, I'll clean this all up, I'll give you some rigorous proofs. And the physicists are no longer interested, they're sort of on to the next challenge. In this case, it happened differently. They met on the common frontier. What the physicists were doing and what mathematicians were doing were both at the frontier of their subject, at the advanced stages. So there was really excitement on both sides. The physicists didn't just go away, we know all this. They were the same level as us, and that actually was a different experience from earlier times when the physicists were usually ignored. Mathematicians, they say, you guys, all you do is come and lay the foundations after we've built the skyscraper. So yes, it was a different phenomenon then.
What about the geometry, going back further? Were you always interested in geometry, or did that develop?
I was always interested in geometry, I think. But it depends on your definition of geometry. People like Plato, as I say, God was a geometer. I mean, to me, geometry encompasses most things in mathematics. As you get broader, you simply bring it all in your empire. So, but I was always a geometer. I think when I was at school, my last year at school, I was very enthusiastic about projective geometry, good old-fashioned projective geometry, which is a beautiful subject, and which became out of fashion very soon. Shortly after I went through the school, people said, too much geometry is taught in schools. Throw out Euclid, give them algebra or computer science. So, but I was old-fashioned geometry. I loved geometry, And then I went to university, we had to learn other things, but at the next stage when I got a chance to learn the geometry at the next level, I took it up, differential geometry. So I was always, I think, a geometer in that sense. I enjoyed geometrical things. I liked, but under very different headings. They could be part of analysis, they could be part of algebra. But I always enjoyed, and I think that's a matter of partly personality and temperament. I like to sort of see things. I mean, it's not literally, of course. What you see is a mathematical symbol or imagination attached to some mathematical object, putting it in pictorial or quasi-pictorial terms. So it's way, but as I said before, I think the visual skills of the brain are enormous. We can see, and if I look around, I can absorb a vast amount of information in a fraction of a second, and I know what it means. And that's because the brain has been tuned over evolutionary history to do that, be very good at it. And whereas things involving in computation on a piece of paper or algebraic and manipulation, we didn't evolve to do that. There was no evolutionary advantage. If you beat a monkey at writing out a formula. So therefore, our brains still think in a fundamental sense visually. And if we can use that to help our mathematics, it's a very great advantage. And it's a mistake to say that geometry only deals with certain things and the rest of it is symbolism. You've got it the other way around. You've got to try to take anything you've got and put it into pictorial form so you can get some imagination way of thinking of it. And in that sense, I'm a broad-minded geometer.
Topology was a rapidly developing subject in the 50s and the 60s, but you started more of as being an algebraic geometer, I suppose, coming from the classical side. So
I started as a classical algebraic geometer, but I worked with my teachers, Hodge and Todd, both of whom were on the sort of modern fringe of geometry. They'd both been involved with things which subsequently we recognize as topological aspects of algebraic geometry, Hodge theory. So I was on the sort of a good position from that point of view. I came from a classical background, but moving towards the new frontiers, and there was a lot of topology around at the time when I was there in Oxford and elsewhere, where new topological ideas, and when I went to Bonn, Innsbruck, a lot of new developments which were in the frontier zone between algebraic geometry played a big role in the early development of some aspects of topology. All the stuff that happened in Bonn and Arbeitstagen, all about characteristic classes and numbers and forms. That all was large parts of it was motivated by algebraic geometry. So I had the right background for that, and I wasn't trained as a topologist in the sense that a lot of other topologists at the time were in formulas and homotopy theory. But I came with a very good view of how topology relates to algebraic geometry, and that's still a very important part of its role.
Was your first work in real algebraic topology, was it K-theory, and why that particular subject?
Well,
if that was first.
It's difficult to remember. I mean, basically, K-theory came out of algebraic geometry. It was Grothendieck's ideas, because this was algebraic geometry, through sheaf cohomology and so on, and then Grothendieck came along with he introduced K-theory. I picked it up and put it back into topology because of instant interface. I saw that it could be useful, combining that with topological ideas. So it was very natural for me to latch on to K-theory when it came out. I obviously may even have written some minor papers on topological aspects a bit before, but in a minor sort of way. But K-theory was the natural frontier zone between algebraic geometry and topology in that period, centering around Grothendieck and Innsbruck. And I was one of the first people to be, fortunately invited to take part in these early meetings when all the ideas were being thrashed out. So, that launched me in the right direction. I was fortunate to be the right chap at the right time, and I was used as things go.
Mm-hmm. Now, one of your major achievements was the index theorem, which also taught you from geometry and topology into analysis. So how did that begin?
Well, again, it was a sort of continuous movement, because it's not quite right to say. See, algebraic geometry always had the aspect of complex analysis in it, going back to Riemann, and in the great expansion after the war, sheaf cohomology by Serre and Cartaya, that was formalized in a big way. Complex variable theory so that branch of analysis, complex variable theory, was part of the tradition of algebraic geometry, and I learned it, and I learned the new stuff. So I knew all about the D-bar operator and all that. What the new bit was having to sort of move from that to real differential geometry, where you didn't have any complex structure and you had to write down differential equations, but via the Laplace operator, that's not that far away. You had to make there were 2 or 3 key steps that had to be reached, one of which you had to get away from the idea that you had sheaf cohomology groups in every dimension, and you had to focus on the difference between the odd and the even ones, and have a single operator that does that, which was the famous Drakh operator. And once we realized that, then we got involved with real analysis, but it was kind of real analysis so close to complex analysis, it wasn't a totally different field, and you had to learn a little bit new terminology, but it's really quite old analysis, potential theory, elliptic equations. So these were, interesting enough, the big barriers to progress or to make were not technical things, not how did you get into analysis from algebra. They were the conceptual thing. Why did you think of going into different real geometry? What made you think that this was a productive thing to do? And that was actually takes much longer for that to happen. Learning the technique is comparatively easy part. There are textbooks or experts, but knowing what question to ask and why you should be thinking this way, that's actually there's no rules for that. You just have to pick it up and make good guesses and say be at the right place at the right time, have a bit of inspiration. Very unpredictable pattern. So things don't work in the way that subsequently people look back and say, oh, this was the obvious sequence of events. Yes, but the obvious things, the bits that look obvious now, were the bits were hard at the time, and vice versa.
How did the big question arise between you and Singer? I mean, did you have an idea about what the format of the theorem should be, and when did Singer become involved in it? Did he start it? What was the story?
First of all, a caveat. One's memory is always selective. You remember what you did, and you tend to forget what the other guy did. And I'm no exception to that. Freud was very, very good on these sort of things. You suppress the things that other people did, and you highlight your own contributions. But let's see. The point was that we started off with algebraic geometry. We had this famous Hessenbrook-Riemann-Roch theorem, which is the culmination of a century of mathematics, beautiful theorem, fantastic result, greatly general. And then K-theory came along, Grundig, and pushed it even further. This was tremendous stuff, and we all knew it. What motivated me was what appeared like a small sideline. Amongst all these formulas that Hessenbrook generated, there were the famous formulas which calculated the dimensions of spaces of solutions, sheaf cohomology groups in terms of topological invariance. But then he manipulated the topological invariance with a great deal of formal skill. And so sometimes you work out a formula where the answer, which appears to, on face of it, be a rational number because it has denominators, is actually integer because you express it as the dimension of a certain vector space. But sometimes it comes out to be integer without a vector space. You don't know where it's come from. So that intrigued me. And so we were trying to identify what these missing integers were that was predicted by the formulae. And we had a lot of clues. We knew it had something to do with spinors. We knew the formulas for representation theory. And we knew the shape of the answer. And so eventually we could see what the answer was. We didn't know the problem. And we were looking for the problem which had this answer. And I was thinking about this a long time, and then Singer was visiting Oxford at the time, and we started discussing, and I said to him, there should be something which explains this. And then he came out one day and said, well, I think I remember what it is. It's the Drakh operator, which comes from physics, and he'd done more physics than me. I had been to Drakh's lectures, but couldn't remember much. But he'd done a bit more, and differential geometry, and the two together produced the Drakh operator. Once we saw the operator, it was all done, because we had everything waiting for it. We were waiting for the emitting thing to drop in. We had all the ground prepared. We knew how it would slot in, how it related to complex variable theory. We knew the answer. We knew lots of examples. We had everything. And, well, after that, we had proof. But as I said, the proof is the comparatively trivial part of this operation. It took a few years to produce, and then we produced lots of different proofs. There's no one proof. So the proof is the last stage in the operation, but the missing bit was to get the right point of view and to ask the right question. And took a surprisingly long time, well, in retrospect.
So was the Drakh operator not in the air before Singer brought it up with you?
The Drakh operator was introduced by Dirac for physics.
Yes.
He explained the quantum mechanics of the electron, and particularly that's in a Minkowski space, which is a relativistic framework. It had been generalized, physicists who knew about this to curved space-time, but never been used by mathematicians, to my knowledge. There were no mathematicians. Hodge, who'd done differential forms, harmonic forms. Dirac did the Drakh operator. They were in the same department. They were colleagues for 30 years, but they didn't actually talk to each other about mathematics. If they had done, I'd have been out of a job, because my job was to fill in what they could have done together. But they didn't. So nobody actually had introduced the Drakh operator in geometry at all. Once Singer pointed it out that you write it down, well, maybe other people thought of writing it down, but didn't do much with it. What can you do with it if you don't know the motivation? Maybe some people like Klenovich knew about the differential geometry. They would certainly know about it from the point of view of curved Lorentz space. But in Riemannian space, nobody ever thought, now what good's a harmonic spinor to anybody? Harmonic forms had a relation with topology, but, well, Nigel will tell you that his first thesis was really to investigate harmonic spinors and see what one could. Now, why were they, given that they didn't have any natural relationship with topology, what good were they? So it was that realization that set things going. But mathematicians had, so once we brought it in, of course, mathematicians took it up. Once they'd seen what he could do with it, then it became popular, it became fashionable. And after a while, when people look back now, they say, well, it's obvious, why did these guys take so long to find it? It's trivial, and it is in some sense trivial. You give it a graduate course, it's almost the first thing you could do as an exercise. But when you're evolving this theory, it doesn't look that obvious at all. It never occurred to you. And the reason is fundamentally that spinors are still mysterious things. Nobody, I think, understands what spinors are, I claim. Not the physicists who use them for the electron, not the algebraists who use it for representation theory, not even the geometers now start using it. They don't really have a good feeling for them. They don't know what they mean. They use them, and they're obviously very fundamental. But and there's a nice passage in one of Hermann Weyl's books when he says that only at the level of spinors do we really reach that depth of understanding of Euclidean geometry, which goes back to the Greeks. It's a beautiful passage, but very hard to decipher. But anyway, I claim we don't really understand, in some strong sense of the word, what spinors are. And so it wasn't surprising in a way that it took a while for them to be introduced. What were they for? They're now, but they're only a tool. People learning more about them, and there's ways in which you can get better understanding. But it still remains a bit of a mystery. They're one of the deepest mysteries in geometry, I think. In a way, I like to put it this way. It took years, centuries, for mathematicians to understand the square root of -1. Okay? Hundreds of years, people had they had this number, square root of -1. It didn't exist, but it was very useful to use it. You got marvelous theories, and eventually, after 200 years of use, it became respectable. Gauss gave a definition, and modern complex variable theory was accepted, and that's fine. Now I claim that spinors is like the square root of geometry. Geometry involves things like lengths, areas, volumes. And spinors involve the square roots of these things. Now, that's a much more difficult notion than the square root of -1. And it'll take us several hundred years, I claim, to understand what the square root of the geometry really means. I mean, you can put it philosophically, you can see why I like to put it that way to point out the kind of issue it is. The square root of -1 was a serious problem. It was called an imaginary number. It did not exist. It was imaginary. Yet it was damn useful. And look what you could do with it. And then not only was it useful in algebra, it was useful in analysis and the whole physics eventually. And the Drakh operator is with the spinors is to do with the square. Well, the Drakh operator is the square root of the Laplace operator. The Laplace operator has a long tradition in physics and history. But the square root of that operator, it started off with Hamilton with his quaternions, and then with Dirac, to write down the square root of the Laplace operator. That's a good start. But the square root of an operator is not the same as the geometry. The operator is an aspect of the geometry. But square root of the geometry is and we now beginning gradually with one thing and another, with twistor theory and self-duality, we are beginning to piece together some sort of partial understanding of spinors in different contexts. So we're making progress, but give us another 100 years, have this round table in 100 years' time with some of your younger eyes might still be here.
Yeah. Can you explain why the physicists talk in terms of spin up and spin down? I've found this terminology.
Well, Nigel might be able to do better than that. I never really understand. It has to do with the relationship of spin, which takes place in the spinor space, with Euclidean, the ordinary direction in space. And because of the Minkowski space, the light cone has a certain relationship with the spinners, you can identify, and that's why spin, or electron, is related to angular momentum and things like that. So there is a connection between things in space that we see, which are up and down, and things in the spinor world, which are really in a different world. They say they're in the square root world, but there is an overlap, and so the spin up and spin down is part of that dictionary. But maybe Nigel can explain it better, because I've talked to physicists a lot, and they talk that, and at that stage I begin to wonder, do I really understand? I understand in my own way, but when they talk in their way, it's not quite so clear to me what they really mean. I'm gradually getting a bit more confident on that, but
sometimes better not to ask what they really mean.
because they think of it in a certain way, we have it our own way,
Yes.
and you might end up being confused.
Getting back to the index theorem, your first proof of it was a cobordism proof,
Yes.
and yet the sort of definitive series of papers used K-theory. Did you always have in mind using K-theory? So was the first proof a kind of rush job in some sense?
Well, you see, the K-theory was there in Grothendieck's work, and we developed K-theory for topological purposes as a tool. Then the index theorem for the Drakh came up to give the formula for the Drakh operator. That was for a single manifold. It wasn't general Grothendieck theory at all. But K-theory came in two places, you see, and it's important to realize this. On the one hand, if you wanted to study elliptic differential operators in general, arbitrary order or whatever you like, it was important to understand their symbol, their local description by highest order terms. And those are given by, at any given point locally, polynomial functions on the cotangent space, which took their values in the matrices. And for elliptic operators, they took their values in the non-singular matrices. So then you begin to see from there's a close relationship with the homotopy theory of the classical groups. And K-theory comes in to understand the classification of the operators on a given manifold in some topological way. And by using K-theory systematically, you can show that every operator on a manifold, any order, whatever, in K-theory terms, can be reduced to the ones we're familiar with in differential geometry, like the Drakh operator. That's entirely separate, contained to how you prove the theorem about the Drakh operator. It just reduces the general case to the particular case by using these local symbols. And that bit we knew quite early on because we knew K-theory. We knew once we'd learned about the general theory of elliptic equations, Gelfand and people, we knew that one should formally at least study them. And when we saw at once that this K-theory took charge of the symbol and it gives you a formalism, and you could formulate the results in K-theory terms. That didn't give you a proof. Then you had to go back and how you give the proof. Now you had a choice. Cobordism was the most direct classical proof, analogous to what Hitchin did in his theorem, and it gave a proof. But we knew that was not the ideal proof for lots of reasons. First of all, that didn't lend itself directly to K-theory. Secondly, it didn't, much further on, incorporate the Grothendieck different generalization when you don't have one manifold, but you have map between manifolds. That came much later. So we knew that, so K-theory comes in twice. It comes in once at the local level to do with simply the way the symbol depends on cotangent vectors. And it comes at the global level in terms of the analysis. And that's the way, and algebraic geometry, the confusion is that these two things are fused. In algebraic geometry, the fact that sheaf theory, resolutions of sheaves gives you vector bundles, Grothendieck's technique, is a kind of fusion of the two. It takes, on the one hand, it has the local theory to do with the resolution of a point in vector space by a sheaf. On the other hand, it has the global theory of sheaf cohomology. So they're so closely intertwined you can't see them separate. When you go to the real situation, they become quite clearly different. There's the global theory about the operators, which you focus on as you want, on the Drakh operator alone, or you can look at the local theory, and then you'd have to deal with the K-theory of the symbols. And they're really, in a mysterious way, they're different and complementary, yet in some ideal picture they get unified. And eventually when you go into further reaches of the theory later on, well, they get further unified. But it's slightly confusing that there are these two different ways in which K-theory enters, and they were both there, one of them both there from the beginning, different form. But to get the proof of the theorem, we focused on the fastest route. But we knew that that wasn't really the best route. And so we were constantly looking for others to generalize it. We wanted in particular to include the fixed point formula, which I proved for Bott. For isolated fixed points, we wanted to generalize that. And so that led to equivariant K-theory. And so the K-theory began to play a more important role as we went along, and we formulated it more abstractly. But it was, the interplay between the two was an interesting, and it took a long time. It was probably 10 years covered the span of the time I and other people spent on variations on the same theme and the same formulas and different proofs and different methods and so on, yeah.
So collaboration has been a feature of a lot of your papers.
Yes.
What makes a good collaborator for you, anyway?
Well, a good collaborator for me is somebody whom I collaborate with. And that's not so trivial. They have to have the same fundamental point of view in mathematics. You know, what they must find interesting, what you find interesting. They must have the same aesthetic values and judgment. They must have the same kind of perspective, looking to the future, what they want to uncover. That's important. Without sharing a common philosophy, you might put it, you're not going to get very far. They may help at the technical level. So I share with, I think, all the people I collaborated with. Secondly, it's important that each party to the collaboration brings a different perspective. You have to have the same philosophy, but a different background. You must have different expertise. You know, one of you is good at spanners, the others are good at screwdrivers. You want to get the best of all worlds. So my collaborations with both Bott and Singer, Bott was much better. He was better on topology than I was. He knew more about Lie groups. Hitchin knew a lot more about Lie groups and coordination theory. Singer knew a lot more about analysis in general. And then my younger collaborators like you and Graham brought other expertise. So it's important that the collaborator has something to contribute. And so when you write a paper, sometimes you do one bit and the other partner does the rest. Usually the collaboration is so intimate that by that stage you can do it either way yourself. But the technique and the sort of understanding and the background is what you're sharing, what you're exploiting. Why you can't do it on your own. Also, I mean, the advantage of having two people or three people collaborating is that you see around the corner. You come up walking, you hit a blank wall. If you're coming from that side, you can see there's a way around. When you hit an obstacle, a collaborator may be able to see the way around it that you don't see, and so you get on faster. So that's sort of common practice. You'll have multiple points of view. But the combination of a shared philosophy, and also I think it's important that they should be congenial companions. You know, mathematics is a very lonely game. If you play it entirely by yourself, you can do like Andrew Wiles, lock yourself in your room, sit back there for 7 years and come out with the proof of the theorem, or fail, as happened with my friend Papakyriakopoulos, who spent his life trying to prove the Poincare conjecture, and was a solitary thinker and a deep thinker, but he didn't succeed. So you're putting a big gamble when you're devoting your entire life all by yourself to solving something. It's lonely business, and so being able to collaborate takes you out of your hermit's shell. You talk with people, it keeps you sane, which is serious. A lot of mathematicians wander over to the edges of some kind of insanity, literally, and so it helps to keep you in touch with the world, therefore the social aspect, being good terms, and be able to share a glass of beer or a bottle of wine, or go on beach holiday together, or whatever it is actually important part of the friendship, and you become friends, of course, with your collaborators, and that's part of the nature of a good collaboration. So it's a human collaboration. It's not just a sort of technical one. There may be somebody you consult to, how do you solve this problem, but that's not a real collaboration. That's a sort of contract work.
How about a degree of skepticism? Is that important in a collaborator?
Not too much. Well, it does happen. I mean, for example, Raoul Bott, he loved formulae. Until he saw a formula, he didn't believe it. And I was brought up with slightly more abstract views. I say, well, look, Raoul, if we can prove that something is, functorial, if it's invariant under it depends only on the Riemannian metric just before, then it has to be like this. No, until I see the formula, he would do a lot of calculations, check, yes, it works out right, you're right. Till he got the formula, he was skeptical about abstract arguments. And I used to get slightly irritated at the time. Look around, it must be so. But on the hand, later on I learned that sometimes there's merit in the formula. I mean, you learn something from the formula, it's outside the box, which isn't part of what you were doing, and it goes off. And so, so that helped to push me towards including formulae. Interesting enough, see, he's older than me by 5 years. But when I came with younger people, like my student Graham Siegel, he was the other way. He was much more abstract than me. See, so when I was covering with him, I would try to push him towards concrete things, and he would be, no, you don't need this big category theorem. Same kind of tension. Well, it's an interesting point of view. So, yeah, some skepticism, or that isn't quite skepticism in the same sense, but skepticism, which means that you can't prove something because it's not true or it might be wrong. I haven't had much. Most of my collaborators tended to be optimists. They believe that if it looks right. Going back to my teacher Todd, he would do lots of calculation things, and he would say, if there's any justice in this world, this must be true. He would believe in justice in the world, a bit like Hermann Wagner. You couldn't have this beautiful formula if it wasn't true, and that was his sort of. So I inherited a bit of that. If I find a beautiful formula, it had to be true, and most of my collaborators tended to go along with that. Although I do remember one occasion when, with Graham, where he was the other way around. He said something can't be. I suggested something. He said, no, it can't possibly work. It wouldn't work at all. So I got put off. And I came back to it later on, and it did work. So then I explained to him, I told you that all along. See, like my Freud. You could convert from being skeptical to being an enthusiast overnight sometimes. But no, I don't think I don't. Well, there are skeptics outside, from people I didn't work with, who say, oh, you can't, this is, won't work, it's so much too airy-fairy. But among my collaborators, we tended to be optimists.
Actually, I read a quotation the other day from James Joyce that errors are the portal of discovery. Now, did that ever feature in your work?
Well, I always just tell my students, you learn by your mistakes. You mustn't take it too serious. You mustn't make mistakes deliberately in order to make progress. But you learn, because if you make a mistake and you can't find out where the mistake is, you sweat like anything, trying to understand why it went wrong. That understanding is then something you learned, you gained. You see something which before you glided over. And so, yes, you do learn from your errors. I'm trying to think of, these are sort of, whether an error is a misconception.
Yeah.
It's a sort of failing to understand something which you should have done, and then when you've learned that, I'm sure there are. And you do. Sometimes you're doing that all the time, at a lower technical level or a more difficult level. You do things, and then something doesn't work, and you go back and look at it carefully. At the simplest level, you go back and find there's some very subtle question about signs, which is always bedevils those people. And then you get into it, you find that actually those signs are really quite delicate and require careful attention, and a few places like that. So yes, you learn from your errors. That's and if you didn't make any errors, I think you'd be inhuman. First of all, you must make errors. Errare est humani, I think, is the Latin phrase. And so, and you learn from the mistakes, because if you learn something too easily, you also you open a book and read it, and they don't find it difficult, you forget it overnight. If you had to struggle, couldn't follow it, then it sticks. So if you don't see the difficulties, or you don't notice any difficulties, then you won't remember. If you had to struggle through, then you really know every step of the way, and every yard is built into you. Yeah, so I totally agree with you. He wasn't a mathematician, but this is a general statement outside mathematics, obviously.
Yes. Maybe we can move on to more general issues. As President of the Royal Society, you had an overview of all scientific subjects and the people that practice them. Do you think mathematicians are different from the rest?
Yeah, well, every mathematician is different. Every other mathematician, every scientist is different in all sorts of ways. So but mathematics is, of course, different from other sciences. In fact, in some places it isn't counted. Edinburgh University, where my wife went to mathematics, you could do mathematics either as part of the arts degree or as part of the science degree. You chose. So, and it's true, that mathematics is both an art and a science, and sometimes people doubt whether it's a science. But my view is always that science essentially uses mathematics, and mathematics without science is difficult to sort of justify or identify. So I think it's, but nevertheless, it's different. You don't have to do experiments. If every physicist, chemist, biologist spends 90% of his time, or the field as a whole, on doing experiments, and 10% of their time thinking about them or theorizing about them. Mathematicians is the other way around. You do 90% of the time thinking, and perhaps 10% of your time doing a calculation or putting on the computer or something like that, or talking to somebody who does experiments. So there's a balance between experiment and theory is very, very different. Mathematics is inherently the ultimate theoretical subject. And so with physics, theoretical physics, the difference is not so enormous. If you're doing high energy theoretical physics, every experiment costs you $100 billion. So there aren't many experiments. You have to wait for 10 years till they build the next accelerator. Meanwhile, you got no choice but to do theory. So high energy physicists are almost indistinguishable from mathematicians in that sense. But to go down to the solid state physicists, the electricians, and a different world, the chemists and the biologists even more. They have not much, very little theory to go on. Well, now they're getting a bit more. So the mathematics is at the one end of the spectrum. The only people who are further out on that spectrum are the logicians. And they, of course, by the back door have become computer scientists. It's an interesting inversion. I mean, there was a time if you trained PhD in logic, he was the one guy who couldn't get a job because he was so abstract. Now they're the guys who were brought up by the computer companies. So the logic became part of computer science and became therefore integrated back into science. But it was a time when you went from mathematics to logic, from logic to philosophy, like Bertrand Russell, people like that. Or then and from philosophy you went into theology. That was the hierarchy. In the old days, theology was actually the pinnacle. That was the ultimate thought in philosophy. And of course, science was called philosophy, was also called philosophy. It was called natural philosophy as opposed to moral philosophy. And so at that time, I still philosophize, and there is still something called philosophy of mathematics, philosophy of science. But mathematics is yes. So, as President of the Royal Society, I was aware that I came from a rather small niche. In fact, when they asked me to be president, I said, "Well, I'm not really a scientist. I'm only a mathematician, and even a pure. If there are some applied mathematicians, I said, well, I understand, but a pure mathematician, I thought." And so I was very hesitant. I didn't say yes immediately. I said I need a bit to think about it because you're so far on the one wing that it's difficult for you to speak on behalf of the whole community, take a central point of view. But eventually I agreed and did my best. And of course, you go back in time. Newton was president of the Royal Society, and in those days, you could be a mathematician and a physicist and a scientist and everything.
Was there anybody between you and Newton?
Well, as president of the Royal Society, I mean.
Yes,
there were one or two. 100 years before me, there was somebody who was a mathematician and president of the Royal Society, who was not very famous, but his name escapes me now. But and then there were, of course, people who were applied mathematicians. Not sure. Kelvin was Kelvin was a physicist, but he was president of the Royal Society. Stokes was an applied mathematician. So people of that ilk were president of the Royal Society in between. But the last one before me was certainly 100 years before, and so they hadn't had any mathematicians, even applied mathematicians. Well, they had physicists. I mean, honest to goodness, physicists, but Clerk Maxwell wasn't president of the Royal Society, but Rutherford, Thomson, and Kelvin, and Lord Rayleigh, they were all presidents of the Royal Society.
Do you think pure mathematics has a healthy future when funding bodies want more direct applications?
Well, I only follow these things nowadays somewhat at a distance. I think these things are phases. I'm sure they go in and out, and some administrator makes a decision and then it reacts badly. I mean, I think we've been through good phases and bad phases in the past. And in the old days, I remind you that mathematics wasn't regarded as a subject which you put a lot of money in for commercial benefit. It wasn't justified on those bases. Then, of course, the numbers have grown much more, So now people will say, well, what do you get for your buck? And so they ask questions, and so there's a beginning debate. The more expensive you are, the more people ask questions. So it's partly a consequence of success, you might say, because mathematics is now more widely studied, more mathematicians around, more help is given by universities. Then people ask questions, and you'll go through a phase where they'll turn against you. But I think those will be ups and downs. My main point when I was president of the Royal Society was try to persuade the mathematical community that their best help came from keeping closely to their scientific colleagues in adjacent fields, engineers, physicists, astronomers, chemists, because these guys know the value of mathematics. They sufficiently mathematically sophisticated. They know that without mathematics, their subject couldn't develop. And so they, in the broad sense, are, and they are of course a large community, and they carry a lot of clout. So if you're on the same, they have it on your side, you can argue a case for mathematics to government, whatever it is. If you go out on your own and say, well, you guys are doing inferior stuff, we do pure mathematics, and we're superior to you, you lose, clearly, because you carry no weight. The weight is carried by the people who are linked into the world outside, also the physicists are, engineers are. So I think mathematics have best bet always say in good terms and working relationship with colleagues in neighbouring, in broad scientific, then they stand a chance. And the scientific community as a whole will back them. I mean, the scientists outside, yes, you say you must support mathematics. We need mathematically trained people. We need advanced mathematics. Some of them, you may get varying degrees of support, but basically they are on your side. And without them, you're really losing wicket. I can use an American, British expression.
Getting back to the mathematics, what do you think are the main challenges in geometry today? And I mean, they differ from those in the 1950s when you were beginning, perhaps. I mean, perhaps or perhaps not.
Well, when I was beginning, I was at a cusp point of the past. It was after the war intervened. Before the war, there was this, well, what I regard as a great period. Hodge theory was a big thing, and I was in that tradition. After the war, there was this fantastic development in algebraic topology and in sheaf cohomology, and people like Serre and Cartan, people in Princeton, Kodaira. There was a tremendous, and Grothendieck, it was a tremendous, exciting period, which launched off new directions, and I was fortunate to be around to catch the sort of drift of that. We didn't think in terms of challenges. I mean, the word challenges, the people would say, well, you have to provide foundations for what all the Italian algebraic geometers did. But that's a dull way of looking at it. I mean, the Italians did good stuff. They didn't have the right tools, and the right tools come along, but modern theory did much more than provide the tools. It provided the whole framework and structure, which was way beyond technical tools. So it enlarged the scope, and it brought in Lie groups as well. Into geometry. So it unified large parts of mathematics, and it was very healthy. And then that set the tone. That set the problems came out. Nobody before had thought about studying differentiable structures of manifolds. It was regarded as topology until Milner came along with these exotic spheres, and then subsequently Donaldson could even bigger. So these problems weren't predicted. Nobody could predict. Nobody thought. Well, they realized that you had to prove something, but they thought the proof would be obvious. You'd prove the obvious. But Poincaré and well, eventually it was proved. But I think the challenge is usually the most exciting thing, I claim, always the unexpected. If you know that there's a problem there to be solved, you know what it is, well, you tackle it. It may take a long time, like 300 years with the Fermat's theorem, and you build up big machinery. But most of the time, it isn't like that. The unexpected things are discovered en route. Well, certainly the things that are most surprising, Donaldson's theory was totally unexpected. Opened up a totally new door, and the relationship with physics, which was intimately related with that, were really totally unexpected. So all the new things coming out of the interplay between geometry and physics are new. But to put them as challenges, I think, is underestimating them. You have to understand what this all means. That's more than a challenge. That's a sort of a philosophical conversion. And that'll keep us busy for 100 years, I think. Understanding what it means, what do you do with it, how do you develop the theory, how much of it is physics, how much is mathematics. We're in the middle of it now. We're probably 1/4 along a century's worth. And so you can see that there are, of course, technical challenges, proving this theorem, that theorem, which are good, local objectives and sometimes focus attention. and those can drive a subject. I mean, Fermat's last theorem led number theorists to develop algebraic number theory for hundreds of years, and led to all sorts of things, including finally the proof. But even if it hadn't led to the proof, it would still be a successful exercise in stimulating ideas. And, well, I suppose the Poincaré conjecture, in some senses, had a somewhat, or certainly three-manifold theory, but four manifolds is still an open. I mean, if you want to know what the biggest challenge is, understand four manifolds. We don't. So there were various times along the way where people thought, ah, yes, Donaldson theory shows it wasn't what you thought it was. It's really algebraic geometry in disguise. Then they said, no, that's not that. Now it's symplectic geometry. And the goalposts keep moving. And not even Donaldson has given up. He says, nobody has a sensible conjecture about what form. Unknown story. How many new kinds of manifolds will we find? How many new invariants will they produce? I think that's the people who know most about it are the least dogmatic about what to expect. Only guys who don't know much say, well, here is a nice conjecture, we should finish it off and prove it. There's no good conjecture, really. I mean, the four-dimensional Poincaré conjecture of smooth manifolds is a little small subset of it, but they won't get you very far. So I think there are particular problems within it. I don't think they highlight this 11th, 8th conjecture or whatever it is. Yeah. So there are technical issues within it, but they just show our ignorance. And I think, so understanding four manifolds in some deep sense, understanding spinors in a deep sense, which may go along with that, understanding the relationship of geometry and physics in a deep sense. What has all this got to do with real physics? Is all this string theory really physics, or is it mathematics? You know, there are people out in the physics world who say, this is not physics, it's mathematics. If you want a job, go to the mathematics department. That's a big problem for young string theorists. And I sympathize with the physicists because string theory stuff is so far removed, any present day an experimental test is impossible because the orders of magnitude is so small or large. Nevertheless, I think the theory still has a lot of physical basis to it, has a lot of interesting connection with cosmology, but where is it going to go? In other words, whether string theory will be an important part of the theory that evolves physics and eccentricity or not remains to be seen. And is it going to be a dominant part or a minor player? Will there be some totally new ideas coming along where string theory is sidelined? All these are big questions which we don't, I think, know. And again, the people who know most about this, like Witten, are the people who are least convinced. There are those guys, whom David Gross is one, I think, they nearly solved the problem. We have a theory, it's called string theory, and we're just almost there, around the corner, Let's wait a year or two. And I think people like Witten realize that's not true. They're close to solving some problems, but I think they realize they've got a long way to go. So I think it's a long way to go. So that's what is physics? Where physics will go is a big problem. And but I have the mathematics that comes from physics, which is absorbed in that is definitely mathematics. And a big mathematical future, even if physicists decide they need something else. That's happened in the past. Physicists produced a theory, mathematicians used it, physicists then forgot about it, did something better, mathematicians went on. Knot theory is a good example. So I think that'll keep mathematics busy for 100 years, trying to understand the mathematics that goes behind that. And I sometimes like to describe that as understanding physicists are doing something like symmetry, nonlinear Fourier transform theory, special geometries. These are all generalizations of previous geometry and infinite dimensional moduli spaces, function spaces. In the old days it's called calculus of variations. You can see old threads in that. I suspect that will go into the big area, and subsidiaries will follow out. A little bit of number theory here, a bit of algebra there. Sorry about that. So I see a very exciting future. I think mathematics is a good place to be at the moment. It's not. Some people will think at any given stage we're nearly finished. Close the door, close the books, pack up, take something else. I think that's wrong.
You've been a geometer, and that's been closely tied to physics, mechanics, the real world. Now biology is in the upswing. Mm-hmm. It's not clear to me what sort of mathematics is going to come out of that. Do you have some views?
Well, I mean, I think one has to express a first of all caution. The fact that mathematics has been so successful in physics and by corollary in chemistry and related things and astronomy doesn't guarantee that it's going to be equally successful in biology. There are people who say that biology is a totally different field. God may have written down the fundamental equations of physics, But with biology, you just lay down the rules and threw the dice, and let evolution take its course. And we are here by a series of mistakes and, well, natural selection, which is not a mathematical form process. Natural selection is mathematical in some sense, but the outcome doesn't lead itself to many laws. Well, if that's true to some extent, the question is to what extent? There are undoubtedly certain fundamental facts of biology which are laws. Genetic code is a very mathematical structure in a way. DNA, it's how the genetics, how things are constrained, and then so that's very definitely as mathematics. But the big question, I think, is, will mathematics play a significant role at some really higher level? And the one place it might play a big role is in understanding how the brain works. Now, the big question for the 21st or 22nd century of biology is, how does the brain really work? And we're just scratching the surface. People know a lot more than they did 25 years ago, but it's just a tiny bit. They really have very little idea. And when they maybe make analogy with computers, it's totally naive. So the brain is actually a much more sophisticated thing that most people working in the field would like you to believe or pretend. The computer scientists think it's just a big computer. The real good people who work in neurophysiology know that they're nowhere near really. They know made a lot of progress, but in the light of what it looked like 100 years later, looking back, that you'll be equivalent to just done baby physics by men. So I think, and that might require a very much more sophisticated set of ideas, which might be mathematical, and the mathematics might not yet have been evolved, probably. But I work with a colleague who's a neurophysiologist, and his view about the brain is that it has a hierarchical structure. It builds on levels of abstraction on itself, just like mathematics. Mathematics is the ultimate hierarchical subject, which is why you can't drop out and come in again. Every level is built on abstraction. I don't like it. I don't like category theory, but and multiple categories. But it is built on levels of abstraction. And my friend said that the brain really works in a similar way. Therefore, there could well be interplay between the levels of the abstractions, hierarchies in mathematics, and in the brain. There are some way which they can be useful templates for thinking. For example, in the brain, well, the philosophers always like to say, what is a chair? A chair, well, there are millions of different kinds of chairs. The fact that the brain recognizes a chair as an object is a miracle, because, well, let's look at dogs. So many different varieties of dogs, yet we see a dog. So the brain has abstracted out the notions that correspond to the objects we see, even though the variety you see is incredibly detailed and different. And they had to do that. We couldn't have survived the evolutionary terms if we didn't know, a lion was a lion, even if it didn't look quite like the other lion. So you had to be able to. So the brain has had to evolve levels of abstraction. That's the kind of first level, getting to the chair level, and to progress. And our success in evolution has depended on our developing a brain that is better and better at abstraction. And so, that very general sense, you might think mathematics might have a contribution to make. It's a mistake to think that mathematicians can go in and say, well, I've got a drawing board for what the brain looks like, and here it is. This is the theory of the brain. Forget it. You've got to start with the experimental data. You've got to look at what you'll know, and you've got to work with all the neurophysiologists. You've got to breed a group of people who can talk to each other, like with physicists and mathematicians, and eventually, this is happening a bit, but it may be a long way to go. So we may be talking about what will happen in 100 years' time. And if that happens, then we will say, yes, there is really a mathematical theory which helps to understand how we think. And then they'll say that's a big mathematical contribution. And all the other stuff will be piddling, nuts and bolts. At the moment, we're still in the nuts and bolts here. Yeah. Although molecular biology has moved a bit beyond that. We're a bit higher up. But, you asked me how I use my biology. I was speaking as an outsider. Mm-hmm. Ask a real biologist.
Perhaps with those 100-year perspectives, it might be a good idea to wrap up now.
Thank you very much, gentlemen.
Oh,
Michael, thank you.
Thank you. We look forward to meeting you in 100 years' time. In this world or the next.
All right. Thank you very much.
Thank you.